Good afternoon. This is one of our last lessons for this sound unit. So there's going to be an announcement for a test soon, just so you're aware. We are looking at range of hearing and loudness, that how loud you hear sound versus the energy of the sound, and the logarithmic scale that's associated with that today. So to get started, let's do a little hearing test. I have it ready to go here. So hopefully you can hear this all right. Try and get my volumes up. So what we're listening for is, if you can hear the sounds, and it's starting at 0 hertz. It goes really fast, so you're not really going to hear you can't hear 0 hertz. You're going to start hearing it around 20 or around 100 or so. But in reality, you start hearing it right away. It's the way the app works. But here we go. I'm going to pause there while I can still hear it. I'm going to pause it once I can't hear it anymore. So it's going to disappear for me, and I'll pause it. Hopefully you can hear it in this recording. Otherwise, just click on the link yourself and do it. But I'll look at the number that I can't hear anymore because my hearing has been around for a little longer and it's been damaged a little more over time and so on. You'll probably be able to hear fairly far beyond where I press pause. So I can still hear that nice and loud. And it went away from me right around there. So if you can still hear past the 12,000, 13,000 mark, either in this video or when you click on the link yourself, that's just evidence that your hearing is better than mine. Hasn't been around as long, hasn't been damaged as much. You didn't have a big stereo system in your vehicle when you're in high school in Sault Ste. Marie in the 90s, stuff like that. What it's doing. I can hear some weird noises going on. Trust this app after all. But hopefully you can hear a real drop off at some point. It was definitely, for some reason, making some increasing and decreasing sound noises afterwards. We could look for other hearing test ones too. You could look for other hearing test ones and go through it. But basically, what we're seeing is that from 20,000 to like the range of human hearing, right, is from there to there, from the 20,000 to the 200,000 range. Okay, so 20 hertz to the 20,000 hertz. That's the range. I think I said 200 by accident there for a second. But that's the range. And then you can see there's some organisms that can hear lower pitch, lower sounds than us. So dogs, that's why they can sort of, they freak out about thunder maybe more before you even hear it, because they can hear that low pitch that travels long distances nicely. And they can also hear higher. So that's the dog whistle range, right? How a dog whistle works is it's literally just a whistle that dogs can hear, but we can't. And so you just train them to, come when they hear that sound. It's just a training thing. It's not that it bothers them and attracts them. You just train them to respond. It's like calling their name just when they hear a sound that only they can hear. So just out of interest, dogs can hear a little bit further each way. There's lots of different ranges of hearings for things you can see on the chart. Okay? So the next thing I want to cover is starting to look at how loud a sound is heard as, how loud it seems. It's basically perceived amplitude, right? So the amplitude of the sound corresponds to the loudness, but not directly, as it turns out. And one of the things it depends on is the frequency. So you might have noticed that when you're adjusting bass to treble, if you have an equalizer like this, you'll find that you have to sort of crank up the lows to make it sound good and crank up the highs to make it sound good. And the reason for that is because we just can't hear the low frequencies as well or the high frequencies as well as we can the middle ones. And think of it just anatomically, that makes sense to be like, this is your outer range of hearing. So you can hear it, but barely on those edges, right? In the middle, you can hear it loud and clear because it's in the sweet spot. It's right in the middle of your hearing range. So this graph is complicated, but these are what are called constant loudness curves. And just generally overall, you can just look at this and see like, this is how much energy needs to go in on the vertical scale to make it sound like a certain loudness. So for example, to make something sound a loudness level of 30, it's 30 decibels. We'll learn about decibels shortly, right? You can see that you'd have to have, almost 90 pressure level in decibels. So basically, think of this as the energy scale, really. Oh yeah, those are just, they don't say it properly, or so I have it labeled, right? The numbers don't mean the energy level, but that's what it's meaning. So you'd have to have an energy level quite higher to sound like 80 decibels or like 40 decibels, I should say, in comparison to the middle, where you can hear it better, right? So you need a lot less energy to have it sound 40 decibels, and then you need more energy over here to make it sound 40 decibels, and so on. So at 20,000 hertz, lots of energy would be needed to have it sound like 90 decibels, for example, right? To be able to hear something at a 90 decibel level, you have to have lots of energy. And then in the 5,000 range, that's apparently the sweet spot that your resonates well with that frequency, so you don't need as much energy in the sound. Something interesting that came up last time I taught this course, I hadn't really thought about it, but what's the loudest sound possible? So think about what sound is, right? Sound is pressure, like pressurized air and rarefacted air, or depressurized, lower pressure air. And so there's a loudest sound physically possible in air, because the air can only support compressions and rarefactions so much, right? So you can't really get anything louder than 194 in decibels. Again, we'll learn about decibels shortly. In water, because the molecules are more strongly bonded, you can actually have pressure waves, sound waves, up to like 270 decibels, so quite a bit louder. So the decibel scale, okay? So we're looking at loudness. dB is the short, deci as in like decimeters or centimeters, so it's little, and then B is capital because it's after the name Bell. Okay, so decibels is named after Bell, Alexander Graham Bell, I guess, I'm assuming. I don't know, I'm not a historian. Anyways, there you go. So decibels, dB, is a logarithmic scale, all right? So if you're looking at the scale here, this is how much energy there is in micropascals. It's just energy. It's basically a pressure measurement, but if you could relate it to energy directly, obviously. So if you're looking at each of these numbers, it's this weird scale where you're going from 0 to 100, let's say, and it's going from 20 to a million. And on the full scale, it's going to like 100 million. And the question is, why? Why do we have this decibel scale? The reason I was told in school, and it never really sat well with me, so I'm putting it in quotes because it's not really a reason. Basically, it was described as there's a really large range of energies possible. And so the logarithmic scale shrinks it down. So instead of going from 0 to 100 million, it goes from 0 to 130, which is nice and all, but it's not the reason, right? So the real reason as to why the logarithmic scale is used, why we quote sound levels, loudnesses in decibels, is because the relationship between how loud a sound is heard to the amount of energy in the sound is not directly related. It's not a direct relationship. It's not a one-to-one. It's not linear. It's not direct at all. Instead, it's logarithmic. It just is. Okay? So the way humans hear loudness is logarithmically, whatever the heck that means, right? Learn about that later in a math class. I'm not requiring it for this course. We'll be able to use it effectively in a physics concept ways, and then later in math class you'll learn more about what it means. It has to do with solving for exponents in math and so on. But so just to be clear here, if you have double the amount of energy in sound, it does not sound twice as loud. Okay, so for example, you can easily picture this. If you had one person talking at 60 decibels and then another person talking at 60 decibels, is that going to sound like twice as loud? You might think it does, but it really doesn't, because twice as loud would be 120 decibels. So 120 decibels is like a ship's engine room, or standing next to a really loud car that's revving like crazy with no muffler or whatever, something really loud, right? Whereas 60 decibels is just someone talking, having a conversation. Um, Even like, two people playing guitar, like it's not twice as loud. It's just two guitars playing, right? So in actuality, if you use a sound level meter, there's apps you can load onto your phone. You can have one person talking at 60 and another person talking at 60. I do this in class all the time, and it adds up to around like 63 or so. It's just a little more than 60 when the second person starts talking. It certainly doesn't jump to 120. So with the sound level meter in front of you, you can talk and see that it's about 60, and then you can like scream into the thing and see that it goes up to like 100 or something. So two people talking definitely isn't the same as someone screaming. It just isn't. Okay, so that's just fact of life for the way we hear sound. So logically, if you have two people talking, the energy is, of course, double. You have two energy sources, and we're going to use that fact to help us work with the logarithmic scale and talk about loudness and how much energy there is. So here we go. We need a way to distinguish between how much energy there is and how loud it sounds, right? So how loud it sounds is your volume or your loudness, right? And so unfortunately, the words are terrible for this that they use. They're so indistinguishable, but just that's the main concept you want to think of. It's often referred to as sound intensity or energy, and then I'd prefer it to just be this, either perceived intensity or loudness. Okay, these are the same things. Perceived intensity, in other words, how loud it sounds, or the volume or loudness. They refer to it for some reason as sound intensity level, which is so close to sound intensity that I get them confused myself. But the main overall concept I want you to be aware of, that we're talking about how much energy there is versus how loud it sounds. Okay, and it's just not a one-to-one thing. You get twice as much energy, it doesn't lead to being twice as loud. It's just a fact of sound. So the units for this would be in like, for energy, would be in like literally in watts. It's in pressure. It's picowatts per square meter. It's related to pressure, and so on. Okay, so it's just an energy value per square meter and so on, right? So the decibel scale, I'll try and help you understand how it works, and we'll get to be able to work with it. So the decibel scale, 1 bell is 10 picowatts per square meter, which is what we call 10 decibels. And so for some reason it was calibrated this way, and so then we say decibels because working with tens is kind of convenient because of the scale. It's around 100, so going in groups of 10, kind of like an easy way to divide it up. So the key points to do with this, an increase, this is huge. Okay, this is a big one, big star for this one. Okay, an increase in sound intensity level in loudness by 10 decibels. So if something is 10 decibels louder, that corresponds to an increase in the amount of energy by a factor of 10, which is different, right? Like adding 10 is equivalent to multiplying by 10. So you can see how the numbers are going to get big quickly because we're multiplying by 10, right? And so it's just been studied and found that this is true. And so we just, someone, I don't know, whatever you want, devised or, worked out this scale, and everybody sort of looked at it and listened to it and said, oh, actually, I agree. That's what things sound like in terms of loudness. And so this is how it works. So we have like a 30 decibel sound increased to a 40 decibel sound. You're talking about 30 decibels, which is, a country park, the breeze is blowing or whatever, and then someone like whispering in the library, right? Going from, country park, birds chirping, to someone whispering in a library. It's a little louder. It's actually, 10 decibels louder, essentially, we could say, right? But it's 10 times as much energy. And then I'm going to do this other factor here. So there's 3 ways we can talk about how much louder something is. We can talk about literally just how many extra decibels it is. Okay, so adding 10 decibels, it's 10 decibels louder. If you want to look at like how many times as loud is it, then you would just do 40 divided by 30, right? It's 1.33 times as loud. Or if it went from 40 to 80, it's twice as loud. The energy though is times 10. Okay, and then since I mentioned the 80 example, let's go from that 40 decibels up to 80. I think I have this later on in lesson 2, but so if I went from 40 decibels up to 80 decibels, obviously it's an extra 40 decibels, so plus 40 dB louder, right? It's twice as loud, so it is, let's say, times as loud, just like I did there, and it would be the 80 divided by the 40, which is equal to 2, so it's twice as loud. And then if you look at the going from 40 all the way up to 80, right, we would increase to 50, 60, 70, 80. So each add of 10 is multiplied by 10. So add 10, add 10, add 10, add 10 in decibels corresponds to a times 10, times 10, times 10. So we're talking about times 4 zeros, right? So 10,000 times as loud, as much energy, sorry. As much energy. Squeezing that in. Okay, that's how it works. But I'm afraid I might have that exact same example here, but here we go. So obviously, like I said, it's 40 decibels louder. So it's twice as loud. So 40 decibels louder or twice as loud. And then times as much energy is exactly what I showed there. When we add 10, add 10, add 10, 10, and so on. For each one, there's a multiply by 10 factor. And so clearly it's this many times as loud. Okay. When we start to look at the result in the end, if you look at how 10, the one with the 4 zeros can be written as 10 to the power of 4, right? And so the pattern we're going to notice, and I'll just get going on it right now so we can see it over and over again. Okay, maybe I'll do this one first. Okay, so this one here, if we were to go through it, we have obviously it's 50 decibels louder. It's the times as loud to be 90 divided by 40. Just how many times extra is it? Second divided by first, right? So 2.25 times as loud. And then we have the 5 plus 10, so we have 5 times 10, so it's 10 to the power of 5. Okay? So what you want to notice is the connection between this end result, this number 10 to the power of right here, how it corresponds to this 40 decibels louder, in this case, the 5 and the 5 decibels louder. Okay? And obviously it's the same number, it's just divided by 10, right? So basically you can look at this and say, okay, well, we've got 4 groups of 10 bigger, right? And so, we have this 40 number. It's 4 groups of 10, so that's why it's 4, right? But if you're working from the 40, you can just say, 40 divided by 10 gives us the number that's the power of 10. That's just working with the logarithmic scale. Okay, so for this one, we have that it's 50, and so we're going to do 50 divided by 10 and get the 5. Right? The reason that's necessary, it's not just a nice shortcut, it's actually necessary because you can do a question like this as a result. 76 decibels up to 93. Obviously, it's not a nice grouping set of tens, right? And so you can't just do the times 10 times 10. It's like times partially at another 10 or something. So if you look at extra decibels, it's 17 extra decibels, which is a plus 10 and then part of a plus 10, right? So it's going to be like a times 10 and then some more. So how much more? Well, the actual times and loudness is this 93 divided by 76. The factor of energy increase is 10 to the power of the 17 divided by 10. Okay, so it's just the 17 divided by 10 gives a 10 to the power of 1.7. So it gives us 50-ish times as much energy. So there's your times 10, right? And then extra. Times 10, must have been times a 5 as it worked out, just in the logarithmic conversion there. And that's one of the things we can do with this. Before we go on to the best thing we can do with this, I'll just give you some other facts here. It's a human calibrated scale. So the lowest sound a human can hear is 1 bell or 10 decibels. 0 bells, weird thing here, 10 to the power of 0 means 1 picowatt per square meter. So 0 decibels is not 0 energy. It's kind of a strange thing. So then you can have negative decibels because negative decibels mean less energy, right? So it's a weird kind of result of the logarithmic nature of how sound is perceived by humans. So negative decibels is a thing. And so, and the smallest volume difference detectable, people play two sounds and tell me yes or no if one's louder or not. The smallest detectable on average is about 0.1 bells or 1 decibel. This isn't a trivia course, it's just kind of for interest, right? So just thought I'd mention it. So back to this, like I said, coolest thing that I like to be able to do with this is if we look at, say, two sounds sounding together, right? That's not going to sound like 140, right? If you use a decibel meter. So it might sound like 74 or something like that. It's certainly not 140. So what we're going to do is we're going to say, well, logically, the energy is double, right? So it's going to be a 10 to the power of a 2 factor. Well, sorry, the energy is double. I apologize. So this answer here needs to be 2, right? And so what we're going to do is we're going to guess and check to see like what power of 10 makes the answer be 2, right? And so we would just literally just use a calculator, whichever type of calculator you got there, where you can do an exponent. And if you did, if you mistakenly made a guess, like I almost did there for a second and did power of 2, obviously it's like, whoa, that's way more than double. It's 100 times as much energy. Then you're like, oh, 10 to the power of 1, that's just going to be 10. 10 to the power of point something, right? So 10 to the power of like 0.6 gives almost 4. So 10 to the power of 3, sorry, 0.3, 10 to the power of 0.3. You just keep guessing. Oh, 0.3 works pretty good, okay? 1.99. So we're basically saying, okay, well, that value ends up being like 10 to the power of 0.3 or so. So 10 to the power of, by guessing and checking, 0.3. Okay, gives the 2 like it should be, right? So that 0.3, we're going to use the way we talked about how the number of extra decibels, right? So extra decibels divided by 10 gives that number, right? And so if you think about that as an equation, the thing you're looking for divided by 10 gave 0.3. So if we multiply both sides by 10, we can solve for the actual extra decibels. So that means extra decibels in this case is 3. So extra decibels equals 3 dB. So we're looking at like 70 plus 70 heard together basically sounds like equals or sounds like, right? So 70 plus 70 is going to sound like around 73 decibels. Okay, it's just the way sound works. Okay. Yeah. So that's the guess and check page to do with this, right? If you're looking at all the different numbers, getting ahead of myself here. But yeah, 3 works out to be pretty close, 3, 1, whatever, right? And so, yeah, that's the number. And then we know that decimal comes from the dividing by a factor of 10, right? So we undo that, we multiply it out, you get the combined loudness. Hopefully that's making sense. It takes a little bit of getting used to. This video here, the Learn to Fly. I wonder if I can probably just click on it. It's probably going to ask for an ad though. Let me see if I have it handy here. Videos. Learn to Fly. Have it. Not searching for me. I don't know why. Here. I think my keyboard isn't responding. There we go. Learn to Fly, Foo Fighters. So this was 1,000 people, all like there. It was a ploy. It was a promotion to try and get the Foo Fighters to come and play their town. And so they made this viral video of 1,000 people rocking out to play a song. So they have a whole bunch of guitarists, a whole bunch of drummers, a whole bunch of bassists, a whole bunch of singers. So I see this And I'm automatically, well, I'm sure some people probably think like, oh man, I wonder how loud that was, right? And so, if each person was making a sound level of like 90 decibels, they're rocking out. That's pretty loud, right? Is it 90,000 decibels? That's more than what's possible. So definitely not, right? And so the way we could figure that out is we just say, well, how many times as much energy is it than one person? It'd be 1,000 times as much. So it's pretty easy where you're like, okay, 10 to the something makes 1,000. Well, that's 10 to the power of 3, right? And so 10 to the power of 3 makes 1,000. And so multiply that thing by 10, and you've got, oh, it's going to be an extra 30 decibels. So the 90 decibels would add up to 120 decibels. That's, of course, if all of the sound, oh, you might not have heard that. Oh, yeah, you did, because I played it on my own little video. I was afraid I played it on Google by accident. Yeah, it would sound louder, but it's not going to sound like 90,000 decibels. That's just actually physically impossible. Yeah, so all these practice questions, the same ideas as before. This one's already been done, I guess. But if we went from 27 to 42, how do you do that? Well, you just say, well, it's an extra, how many numbers here? So it's you subtract the two, and it's an extra 15 decibels. If you divide the two, you can say it's this many times as loud. It's the amount of extra energy though is the 15 divided by 10, and then it's 10 to the power of that number. Okay, so it ends up being like 31.62 times as much energy. Okay. If we had one guitar producing 60 decibels, and then we had 5 guitars playing, how loud would that be? Right? It's not going to be 62 times 5 decibels, that's for sure. It's instead going to be 10 to the power of something gives a 5, right? So 10 to the power of something gives 5 times as much energy. And you just guess and check and see what you get. 0.7 by guessing and checking. There is a way to do this with a logarithm button. So that 0.7 there, just basically to show the idea, if you do log 5 divided by log 10, so you might be wondering what that does and so on, but it's logarithm scale, and so it's to do with this. We do log 5 divided by log 10 gives that 0.7 number. And so if you're interested, the mathematical version of this would be to say, okay, well, we've got our 10 to the power of our variable we're looking for equals 5. And so if you take log of both sides, it's a mathematical operation, is do it to both sides. It actually has this weird property that it moves the exponent down. And so our next line would be, the thing we're looking for, log of 10 equals log 5. Well, squeezing it in there, barely, and not quite really. So then we just divide log 10 on both sides, and that's what I did on the calculator, log 5 divided by log 10. So that's just using knowledge that I have from previous math classes that I've taken and taught and so on, about solving for an exponent using logarithms. But for the purpose for this class, it works where we just say, okay, well, I understand how the decimal scale works, and so we're just going to apply it more logically with just trial and error. We know that this 10 to the power of is really the extra. So that is the loudness scale, logarithmic scale, and range of hearing, and so on. And yeah, so that's it. If you have any questions, let me know, of course. Go ahead and post in the help section here if you have any questions, is the best way, or email me, preferably with the email version, or you could even email my regular school email, right? greg.horn@ucdsb.on.ca. Either way, I end up answering in that post section. So I prefer the post help section because then I can just answer it there. Anyways, it's all good. I'll answer your questions either way. So that is it for now. Talk to you later. Thanks for watching.